For today's lesson, we're going to be talking about binary conversions, specifically converting between decimal, which is a base 10 system, and binary, which is a base 2 system. This is going to be very helpful in networking, as many network addresses, IP addresses, we need to convert between binary and decimal and back in order to calculate broadcast addresses, network addresses, and available host addresses. It also will be used in subnetting networks. So a good chunk of chapters 7 and 8 for the grade 11s, and then used throughout grade 12. So we did a little bit of binary conversions in grade 10, but I'm going to remind you of what we did. So when we're looking first at decimal numbers, these are the numbers we're familiar with, something like 387. Nice, easy number that we've seen before. The value of the 7 is 1. The value of the 8 is 8 tens. The value of the 3 is 3 100ths. Those numbers come, as we said, because it's a base 10 system, from 10 to the 0 being the first place value, 10 to the 1 being the second place value, and 10 to the 2 being the third place value. 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100. So that's where we get our place values from. When we're looking at 387, we know there's 3 hundreds, 8 tens, and 7 ones. So that's a pretty basic way that we look at this number in base 10. Some other things we want to note about base 10 are possible values for a single bit or a single digit. So if we look at 3 as a single bit, we could also call it a single digit. We know the possible values we could put in that place could be anything from a 0. We could have the number 0387. We probably wouldn't write it like that, but we could write it like that. To 1, 2, 3, 4, 5, 6, 7, 8, and 9. If we were to go up to 10, we would end up with a 10, which would be 2 digits, so we would need to add in an extra bit. So this can go anywhere from 0387 to 9387. Didn't leave myself enough room there. So we have a total of 10 possible values for each digit. Now, when we're looking at binary, we're looking at 2 possible electrical states, so either on or off. And when we look at on or off, we're looking at 2 possible values, 0 or 1. So you often see binary along the lines of 1, 0, 1, 1, 1, 0, 1, 0, something like that. And we will be able to convert this 8-digit or 8-bit number. So if we look at this, there's 8 bits at the end of this lesson. So we have our 8-bit number, and it has binary possible values of 0 to 1. Similarly to when we did 10 to the power of 0, 10 to the power of 1, the base values, we're going to use that to find out the value of each bit. So the furthest to the right bit is going to be 2 to the power of 0. Then we have 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. We're just counting up in exponents here. 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. I ran out of room for 8 bits, but we'll get to that later. So 2 to the power of 0 is 1, as any number to the power of 0 is 1. 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, and 2 to the power of 5, 32, and 64. So here we have a 7-bit number with all of the possible values for those numbers. You'll notice that each time we're really just multiplying by 2. So if you can't remember off the top of your head quite quickly what 2 to the power of 5 is, that's fine as long as you can multiply 16 by 2, which gives you 32. So this is not unsimilar from when we did 1 times 10 and 10 times 10 to get 100. So looking at this value, or these possible values, we can fill in binary digits. So let's say, for example, that we're only looking at the first part. So we are only going to look at these 4 possible digits. And on those digits, we're going to say we're looking at the number 1010. So in this case, we know that we have 8 plus no 4s plus 2 plus no 1s. So this simplifies, we can cancel that and that because they're just 0, we're just adding 0. So we get 8 plus 0 plus 2 plus 0, which is really just 8 plus 2, which gives us 10 in base 10. So that's the decimal conversion. So 1010 in binary, as we saw here, is equal to 10 in base 10. If that went a little fast for you, we'll do it again. So I'm gonna widen out my screen a bit here, and I'm going to add in a bit of a longer number. So we know that we want 8-bit numbers because a network octet is 8 bits. What do I mean by that? I mean, if I have a network address you've seen before, like 192.164.140.0, then each of these is represented by 8 binary digits. So if we go 192 is going to be 11000000 dot 164. So to get 164, I'm going to just use the Windows calculator to calculate it to binary. Okay, so the value that I'm going to get there is going to be 10100100. I'm going to also convert 140 to binary using the Windows calculator. You just need to make sure you switch it to programming mode in order to use the Windows calculator. So for this one, I'm going to get 10001100. And then for the digit 0, that's a nice easy conversion. It's just going to be 00000000. So what you'll notice here is that a single IPv4 address contains 32 bits. And those 32 bits exist in 4 what we call octets. So octets, like a stop sign, oct, have 8 possible values. So 8 possible digits inside of that value.